Hello everyone, once again. Welcome to the vCIES 2020 workshop for the network data analysis and visualization. My name is Byoung-gyu. This is the second video clip, and from now on, we'll practice how to analyze network data with software packages of igraph in R program and Gephi. Both are free and open source for the data analysis. Now it is time to practice. Before using the softwares, I will briefly introduce various network analysis softwares and tools. Also, I will introduce briefly about igraph and Gephi software tools, which we will mainly use for the network analysis and visualization here, and explain their strength. There are plenty of options available for you if you'd like to do the network analysis. Firstly, UCNet must be the easiest options you can take. But it is not free and does not support macOS versions, so you may need caution before choosing it. Pazak is also well-known software package dedicated to the network analysis, and even it is free. I think Pazak is a good software for the network analysis. It is regularly updated and compatible with Mac under certain conditions. And the Cytoscape is also a great tool, and it tries to integrate with R and Python. And NetworkX is a Python package. If you're good at Python language, you're good to go with it. But I don't think that many of the social scientists are comfortable with using Python language yet. If you're interested in an egocentric network at a smaller scale of network, EgoNet is a perfect option for you. But if you think you are interested in large-size complex network, you may need more than that. In this practice session for the network analysis and visualization, we'll primarily use igraph package in R program. igraph is a network analysis package available across various computer languages, such as C, Python, and R. It is specialized for efficient and fast analysis of the massive network data. In the R program, there are other packages supporting network analysis functions like tidygraph, ggraph, and base network and network D3. But still, the igraph is the most comprehensive and popular package for the network analysis, as the other packages are only recently developed. But maybe in the future, if you are comfortable with our software tool in general, you can move into the other packages or even combine these packages for your own research. Gephi is another tool we'll use for our network data analysis and visualization. In particular, Gephi is specialized for exploratory visual analytics. It also supports big data analytics dealing with large network having more than 20,000 nodes. The user interface of the Gephi is pretty much easy to learn, and its visualization is much better than the other software tools. The pictures here in this slide are the outcomes from the network data analytics using Gephi software. In an aesthetic sense, Gephi is one of the best options, providing an excellent beauty of the network visualization. And let's start the network data analysis with igraph in R program. First, you need to install R and R Studio. You can download R program and R Studio at the below addresses. If you'd like to know how to install, please watch YouTube tutorials for the download and installation. But you need a caution, as new version 4 was recently updated on April 26, 2020, but this lecture uses 363, so there can possibly be a compatibility issue. The dataset we are using for today's practice session with igraph includes 242 nodes, indicating students of the elementary school. and 8,317 edges, meaning times of temporal interaction measured by their physical proximity. The network graphs in this slide are our final outcome of the iGraph practice session, and you'll be able to create exactly the same network graph at the end of our session. The data source is from the Social Pattern website, which archived many researches studied infection network and network of social gathering and distancing. This archive shares all data set that was used for the research. Amongst many other data sets uploaded in this website. The data set we're going to use for this practice session is from the study of Giamnato, Barrett, and Katoto 2013, titled as Mitigation of Infectious Disease at School, Targeted Class Closure versus School Closure, which studied the infection network at the primary school in France. I choose this data because there must be a lot of interest in contact and infection network inside of the school at the face of school open amid the COVID-19 pandemic. The study was conducted in 2014, but this provides a useful insight on how to manage school to prevent rapid spread of COVID-19 disease, minimizing close contact between students. The contact data was gathered using mobile devices attached to students' body. The devices recorded students' contact for a week whenever students get closer to each other over a certain threshold. Okay, then let me start our data analysis and visualization session using iGraph package inside of RStudio. So this is the script I just prepared for this session. It looks like quite complicated and very long, but you don't need to type in every single lines here because I just prepared the R script file in my GitHub webpage dedicated for this network analysis and visualization workshop for the vCIES. So once you go to this webpage, github.com, Arizona Gongs vCIES 2020 network analysis, which I just leave this link in the YouTube memo at below of this video. And the first page, you can just find the README page with a brief introduction of this workshop and the video and about the data file for the iGraph and expected final outcome as a graph and also about the Gephi software. So to download the R script, just click the first folder here, iGraph, click. And there are 3 files. The first 2 is a data file, and the last one is R script for the iGraph session. And just click it. If you are good at GitHub, you can just literally fork it. You can just directly download this R script into your RStudio using the function of GitHub. But if you're a new beginner of RStudio and GitHub, you can just simply scroll it down and Ctrl+C, Ctrl+V, copy and paste into your iGraph console here. So once you just copy and paste the R script, you are ready to go. So the first thing to do is installing the required packages. These are 4. The first one is iGraph and Radar, Tiger, RColor, Brewer for the visualization. So to execute the command, it's very basic for the RStudio. Just push the button, Control and Enter. I just click No, and the installation is started. Yeah, the installation is completed, so you're good to go. In the first session, there are lots of steps to take for this analysis session. The first thing to do is data pre-processing. Because even though we have a data set, ready-made data set as a CSV file in my web page, we need to convert this CSV file into the igraph object. So the first thing to do is execute the line library so that we can use this readwire package. So I just prepare the data set in my GitHub homepage, web page. So the first one here, named metadata primary school CSV, is a node list. Once you just click it, you can see the data frame here. This is a CSV file. So this is the node list. The first column is the number, unique ID number for each of the students. And the second column, from second column to third column, is node attributes. This is information about the characteristic of each of the students. So the class means that 5 is a grade and B is a class number for the grade. So 5B means that the student number 1426 is a student of 5th grade, class B, and the gender is male. So in this way, we have 242 row, because the first row counted, the column names were counted as 1, so the total number is 242. You can directly download this file into your computer and import the file into your RStudio. But if you're a beginner and it's almost the first time to use the RStudio, you cannot do that because setting directory in RStudio is not easy for the beginner, right? Let me look at the edge list. The primary school is the edge list data set. This is a huge file, so you need to click once more. And there are 2 columns. It's the edge list. So the first one and second one, the student ID number 1558 and 1567, they have a connection, right? They have an edge. These are vertex number, and the meaning that they're in the same row in edge list means that there is a edge between the two. So the source and target is kind of a name for the directed networks. So once you put the vertex in source, it means that the arrow comes out of source and heading to target. But this is undirected network, so it's meaningless here, right? So you can just directly download these files into your computer and retrieve it into your RStudio session. But I just prepare a different way because as I told you, some of the beginners cannot set their directory for the importing. So the way I'm doing here is we can download those data files directly from my web page. So just execute the line, Control and Enter. You can find that we now have a URL object here. So the first URL file must be the node list. So we will create a data frame here. Just execute it. And we got, oh no, this is not the node list. This is edge list. I'm sorry. So just click D. This is edge list, right? It's the same data set we just saw in my web page, right? And D meta should be node list. Let me execute this line. Then we got this file into our RStudio space. So it's the same, right? And the next thing to do is that literally pre-data processing. Because once we just look around this file, the edge number is 125,000. That doesn't make sense, but once you just look at this data, there are lots of duplicated rows. That is because it's a raw data directly downloaded from each of the students on mobile device, which calculate the contact number between the students. It means that the mobile device record this contact and create each of the row whenever they get close to each other. So this means that the student 1326 and 1371 have a duplicate contact. Like how many of the contact here? Like 21 times means that these two students contacted to each other 21 times per week. So that makes sense. But we don't need that much of duplicated rows. We need to create a edge weight here, like a number of contact for each of the student, right? So we'll erase those duplicated contact here, executing this line. So this line, we can create a edge weight column. So we just have a new edge list. It's almost half of the size, right? So now we can see the student 1326 and 27 have a contact number like 27 times per week. But the thing is that this data frame still have a lot of redundancy, because the frequency number 0 means that there is no edge between those two. So we don't need that. And we will erase any of the row, any of the edge list that does not have contact with this command line. So the B1, now we have an edge list of 8,317, right? So we don't have any zero contact here. And there is a frequency edge weight here for each of the edge lists here. So the student 1437 and 1563, they have 764 times of close contact per week. That indicates kind of an intensity of this relationship. They must be really close friends, each other, right? On the other hand, most of the students have only 1 or 10 contact. So now we are ready to go, right? So it's time to create an igraph object. Still, the B1 edge list is not an igraph object, it's just a data frame. So let me retrieve the igraph package here. And when we convert B1, the edge list, into the igraph object studcont, which is an abbreviation of the student contact, and we will create undirected network. That's the reason why we just set a false for the command for the directed, because this is undirected network. And we will add a node attribute that can be retrieved from the meta, the node list. So each of the vertices in this igraph will have a node attribute. So let me execute it. Now we have a studcont. And we will also create a edge weight for each of the edge list, executing this. And we can see the summary of studcont data. We cannot see the whole data set because igraph object is something else. It's not in the data frame format. So it's not visible. This is the language only for the computer, so the human cannot understand this structure of data. But it's really fast and efficient to process this large data set for the computer because it is coded only for the computer, not for the human. But it provides kind of summary of this data. So the first line indicates that this is igraph object, and there's a unique number assigned to this igraph object. So there's a very important information at the first row. So U means that this is undirected network. Once you see the CD instead of U, it means that this is directed. And M means that this is named network, which means that each of the node have their unique ID as a name. And W means that this is weighted network. So each of the edge have their frequency or intensity as an edge weight. And the number 242 is the number of nodes. And 8317 means that the number of edge. So the second line, ATTR, means the attribute. Name is for the vertex attribute, and class, and the V means, again, the vertex attribute. And the frequency, the E means that this is for edge attribute, not for the vertex. And also the weight here. EN means that this attribute is only for edge. And there is a head of the edge list. There's only these several edges because it's a huge data set, like 8,000. So let's see if we are ready for the analysis. We are all done with the data pre-processing. And as a next step, we'll explore our igraph object. So at this step, we will just explore the studcount igraph object we created in a previous session. And we will see the summary of the igraph object, like descriptive statistics. The first thing we can do is executing gsize, which means the size of this network object. So once you execute this one, we can see the number. We could see from the edge list, which means that gsize is the number of edges. Then gorder is number of vertex. So the best way to see the summary information of the igraph object is just executing the igraph object name, so that we can see the node numbers, edge numbers. But more than that, we can just execute gsize and gorder to find the number of node and number of edges per se. And we can also see each of the node list and edge list executing v parenthesis and name of the igraph object and parenthesis. So once you execute this v command, we can see the list of vertices inside of studcount igraph object. And once you execute this line with e parenthesis and name of igraph object and parenthesis, we can see the list of edges. You can also see what are the attributes inside of the igraph object studcount, like with the v and the name of attributes. The gender must be the node attribute, right? So once I execute this line, we can see each of the node attribute for the unique student ID numbers. As we can see from the list, we can see unknown. This is the missing data. These are all missing data. So it is important to look inside of each of the attribute list to see whether there is kind of a missing data or anomaly in data. Then we will convert this unknown into NA to make our program recognize it as a missing value. There's not counting it for the other calculations. And let me execute it. And we can see whether this command was effective. We're back to the gender. And we can see the unknowns are NA, right? All the unknowns are converted into NA. And we also know that in the node list, there is a class as a student's attribute. Once I execute this line, we can see the class information for each of the students. And also, this indicates that there is a kind of unexpected category of teachers. So This network also includes the teachers, which makes sense in terms of the research objectives, just seeing the infectious network inside of school. And the teachers must be kind of a very core of spreading virus because they have a lot of contact with every students. And we can also look this igraph object in an adjacency matrix format. Even though it is not stored as a format of adjacency matrix, we can also see this data in an adjacency matrix format. So I will only see the 10 by 10 matrix, which is only a part of the studcount object. I'm executing. Once I just execute it, there's an indication that this is 10 by 10 matrix. And at the first column, we can see the student ID. And even though it is omitted here, there must be the same student number here. So it will start like student number 1326 as the first column, and second like the same in order in the row. And as I told you in the theory session, for the undirected network, the adjacency matrix should be symmetric, which means that once we draw the diagonal line here, the upper side and lower side of this matrix should be the same. So as we can see from this part, this matrix is symmetric, right? We can very clearly see that. And also, each of the elements inside of this matrix is not 0 or 1. It's, as we remember from the previous part of this video, we assign the edge weight. And each of the edge weight means that the contact number for each of the pair of students. So we can see these numbers here. Now it's time to measure the centrality. In this session, we'll just calculate the centrality measures such as degree, eigenvector, and betweenness centrality we learned in the previous theory session. And we will first start with the degree centrality. To calculate the degree centrality, we can use the function called degree. And we need to set the mode here because in the directed network, they have two different types of degree, as we learned in the theory session. There's an in degree and out degree. But the studcount data, as we all know, does not have any directionality in its edge. So we will just put it as all, which means that there is no direction. So just let me execute it once. Then we just create a studcount degree object. Then we should assign this value into the node attributes, which called the degree. Execute it. And we can see how it was assigned. So those numbers are degree centrality assigned to each of the vertices inside of studcount igraph object. Then we can also identify which vertex got the highest score for the degree centrality using which max function. Execute it, then it just identified that 1551, the student ID 1551 got the highest mark for the degree centrality. This number is kind of an index number, so it does not have any meaning. So we cannot know how much degree this vertex got here, but was identified that 1551 got the highest mark. So by identifying the vertices getting the highest mark on each of the centrality measure, we can just compare that. I just expect that each of the centrality measure may have a different vertices having the high score. Then let me move on to the next eigenvector centrality. We can use evCent function to calculate the eigenvector centrality. Then we can assign this value into the node attribute which is named as eigen. And let's see. The score is normalized only for the igraph package. It calculates the eigenvector centrality using a normalized function. So which means that the score should be between 0 to 1. Then let's identify which vertex got the high score. So in eigenvector centrality, 1665 vertex students got the highest mark, which is different from the degree centrality, right? So in this way, we can see a totally different picture depending on the centrality measure. Then for the betweenness centrality, we can use the function betweenness and set the directed function as false because the default value for the directed is true, which means that it's a directed network, but we are using undirected network, right? So let's assign the value into the node attributes betweenness, and let's see the score here. And let's identify which vertex got the high score. It's the same for degree centrality 1551. And we can convert the igraph object, which got the degree centrality measures as a node attribute. We can convert this igraph object into data frame because the igraph object, with the igraph object, we cannot see the details of the real data set. But by converting it into the data frame, we can just look inside of it. So let me convert it, and there is a df here. So this table is really fascinating. There's lots of columns here, but as we all remember from the start, in a B1 data frame, what we all know about each of the students was the frequency of the contact and their class and gender. That was all about all the information we knew about the students. But after calculating the centrality using igraph package, we got this table. We got much more information about each of the students here. For instance, for student 1326, now we know much more about this student because there are lots of centrality measures which indicates the kind of a network characteristic of these students. We got this information out of igraph calculation. So using these new indicators, we can do the regression analysis or many other statistical analysis. And we got to know much more in-depth and for different dimension of each of the students using these numbers. That's the strength of network analysis, and at the advanced level, you will be able to do those kind of very different kind of regression or the other analysis in connection to the network analysis. And let me start measuring network density. We will calculate the network density here using the function edge density. So as you can see from the console here, the school level edge density is 0.28. And we can also compare this score with the class level density. So I just create a subgraph, which only include the vertices in the first grade class A. Then calculate the class level density here so that we can just compare the density score with the school level density. I just expect the score of the class level density should be much higher. And let me see. Yes, it's much higher, much higher, which almost close to 1. So the density score is kind of the normalized score, which means that the score is between 0 to 1. And the class level density is almost 1. So it means that the students have much more contact inside of the class comparing with the school level contact. And let's calculate observed activity. I will calculate the observed activity based on the class so that I can see that whether students in the same class tends to get more close to each other. But before calculating observed activity, we need to convert the node attribute class into factor. So I just convert it. And I will use the function observed activity nominal, which calculate the observed activity score based on the categorical value. So the types, I just put the values here. Value includes the class information of the students. Then let's see. So the observed activity score is 0.23. But we have no idea whether it's a high or low. So we can just compare the score with the randomly created observed activity score. I just explain further here. First, I will just assign observed activity nominal value. You also calculate it here into the observed activity data frame. The vector here, object here. And I will just create a list. And I will create a randomized sample here. This means that I will just assign the value we created out of the class categories here, node attribute. It means that we will assign these class attributes randomly to each of the vertices like 1,000 times. So each of the iteration, this function assigns the class value to the different vertices. So we can just calculate the observed activity nominal value out of the randomly assigned class to each of the vertices 1,000 times and compare with the observed activity score with the observed activity score here. And let me execute it. Then I just visualize this comparison to make it much clearer. So this histogram shows us that these are the randomly created observed activity nominal score. But most of the score are below 0, which means that the students tends to mingle together with the students with the different classrooms in the randomly assigned, randomly created network. But in our real data set, network data set, we got this high score. It's kind of an anomaly, right? So it means that comparing with the randomly created graph, our data has much higher observed activity score. Now it's time for the network visualization. In network visualization, we will try 3 different types because once we try to draw a network, we need to decide the size of vertex. So at the first case, we will decide the size of the vertex based on the degree centrality of each of the vertex. At the second one, we'll assign the eigenvector centrality to the vertex size. At the third one, we will use a betweenness centrality. So before starting the plotting, we need to set the seed. By setting the seed, we can create the same shape of network for the multiple trial. Once we do not set the seed, every iteration performing the plotting function, drawing a network, it will have a different shape. So prevent that happening, I'll just set the seed. And I will retrieve the library for the coloring, our color bureau, and assign each of the class. I will just set each of the class have a different color by using a brew par and assign a color values into the pal object. And to draw a network graph, we can use a plot function here. Inside of the plot function, we can set the color of edge, the color of line, and also set the label size, and also the vertex size. We will assign the vertex size using pal here. And make each of the class have a different color according to the pal value. And also we will decide a vertex size. And as I told you, we'll use a degree centrality here. But I just divide by 3 for the better visualization. Unless I just divide by 3, the size of vertex should be really big, so there must be the overlapping between the vertices. And also the edge width, I will assign the edge weight for each of the lines, but also divide by 800. Unless I just do it, the line should be too much thick, so the visualization is almost invisible. It's hard to recognize different lines because of the overlappings. And also I just set the shape here. So I'll use a Fletcherman Ringgold. By setting the layout, we can set the shape and also the distance between the vertices. So let me execute it. Then we can see how it looked like. So here we got the graphic. Let me just zoom it up. So this is the graph we just created out of the degree centrality. So each of the size of vertex means the degree centrality score, and the color indicates the class. So those unique color inside of the others means the teachers. So we can recognize there is a clear divide between the classes, right? It's really beautiful. And let me try this visualization using eigenvector centrality. Let's see the change here. So in eigenvector centrality, we can see the vertices, the size of vertices in the middle got much bigger, right? They're much bigger comparing with the previous one. You can see the difference very instantly, right? So we can assume that the eigenvector centrality and degree centrality is kind of very different kind of indicator inside of this network phenomenon. And let me try with a betweenness centrality. It looks a little bit different from eigenvector centrality and degree centrality, but still the shape is the same. So by fixing the seed as 1001, we just produce the same shape of network. Even though the vertex size should be different, every vertex are in the same position. In addition to the visualization of the network, let me just calculate the correlation between different centrality measures here. Underneath that, I just erase that. So let me plot the scatter plot between degree centrality and between the centrality to see the level of association between degree centrality and between the centrality. As you can see from this graph, it looks like there is a high correlation between degree centrality and between the centrality. Then let me calculate the correlation score. It produced, as expected from the scatter plot, it produced 0.8. But this script command must be absent from your R script, so you can just type it by yourself. And let me check out the correlation between degree centrality and eigenvector centrality. I expect a little bit lower correlation coefficient score between the two because we saw a very different size of vertices in the network visualization. So the scatter plot indicates that there is much less correlation between the two comparing with the degree centrality and between the centrality. And how about the score? Yes, as I expected, the score is much lower. So I can say that eigenvector centrality only for this network phenomenon and network data set. Eigenvector centrality and degree centrality shows a very different dimension of this network phenomenon. And now is the last part of the iGraph practice session, is community detection. I'll use a community Leuven clustering as a community detection method. So I'll use a function cluster Leuven to create a cluster object, and I will check how it was assigned. So we got the 6 clusters here, and each of the number indicates the student ID, which shows which students was assigned to each of the clusters. So according to this clustering, we will plot the graph using between the centrality, but this time I will just set the data set as LC, and we'll see how the graph shows a different picture here. Let me execute it. Then here it is. The graph shows kind of binding groupings here and also change the color. It assigned the same color for the same cluster. But it looks like a little bit different from the previous between the centrality graph. So I just prepare the pictures here. So on the left side, you can see the between the centrality are colored according to the class of the student. And on the right side, we got the picture with the clustering. We got 6 different colors, but in this classroom-based picture, we see 10 different colors. It means that according to the interaction, the contact information of the students, we can cluster the whole school into 6, not 10. It's kind of very counterintuitive. And the clustering must be decided depending on the contact pattern inside of school. So each of the school and each of the countries, depending on their school structure and organization of the classrooms and the scheduling, each of the school in different countries may have a different clustering. But this school can be clustered into 6 according to the contact information. I think that is kind of a strength of this network analysis. Sometimes we can face with kind of unexpected outcome, kind of counterintuitive. So I hope you enjoy this session. Even though the coding must be a little bit difficult for the beginners, you can just use this code and just customize it. You can just change some of the key attributes for each of the codings. Then you can create of your own once you find the right network data format, which can be easily converted into igraph object. Now it's time for the Gephi practice for using the Gephi software. You can download the Gephi software from this address, and I recommend you to install all the plugins. Plugins kind of add-on software inside of this Gephi, which just allows a lot of visualization tactics more than the base function. So once you open the Gephi software, you can just click Tools and click Plugins. Then you can find that there are lots of downloadable plugins. For me, I just installed all of them already. So there's nothing in this window for the updates, but you might have lots of plugins here. I recommend you to install most of them. Then you can download a file from my GitHub homepage. You can just click the hyperlink and download the files of node list and edge list. To load a file into Gephi software, just click Import Spreadsheet. And firstly, you need to load the primary school data. This is edge list. As you can see, this is recognized as a edge table. Click Finish. And we all know this network data is undirected. And we need to sum up all the edges because this data set duplicates the same edges multiple times. So we need to sum them up to create an edge list, edge weight. And click Append to click New Workspace and click OK. And now we get 8,300 unique edge cases. It's the same kind of a calculation we saw from the previous igraph session. And then click Data Laboratory. We automatically got the node list and edge list here, but we don't have any node attributes here, so we need to import the node list here. This is metadata. Click Open. It recognizes as node tables. Click Next. Finish. And undirected and sum. And you should be really cautious of checking in this section. It should be appended to the existing workspace where we have an edge list. And click OK. Now we got all the node attributes here. Then let's move to the overview. We need to trim down this huge network set. And I think it's really intuitive because we can walk through just clicking down. Click Node. And we can decide color with the palette here. Click Partition. And we can choose Attribute as a class. and click apply. So the colors are changed to represent each of the classes. And it's kind of messy because Gephi didn't decide the distance yet. It's kind of randomly assigned for each of the position. Then we can cluster. I will just choose force atlas. This is the layout function. In iGraph, we just set the layout function in the plot. For Gephi, you should choose layouts here by clicking each of them and run and stop. So the vertices are gathering together depending on their edge connection. But still the picture is kind of messy because they tend to overlap in a small space. So I will just increase the scaling here and click run. I think I need more space, like 50, and run. Yes. Now we don't see many of the overlaps inside of this network. And click stop. We don't see any labels here in the picture. To add the label, go to data laboratory, and we should create the label column here. So click copy data to other column. You copy the ID to the label. Just click OK. And we got the labels here. Let's check up in the overview picture. I will just click here, node. Then we can see the node in the picture, right? I can decide a size. I will just decrease the size here. Then we didn't decide the size of vertex yet, right? They're all the same. To decide the vertex size, I need to calculate the degrees. So I just click average degree here. And click the size here, ranking, choose attribute degree, minimum size and maximum size, and click apply. So now we can see the size is different depending on the degree centrality, right? They makes the vertices overlaps. So I just run the force atlas 2 once again and increase the size scaling much more, 300. Now it makes sense, right? We can recognize each of the vertices. Also, Gephi supports kind of calculation of the general network features like graph density. Click run, undirect it. And it's the same score we saw in the iGraph analysis, 0.28. And we can also, to create a community, to create the clustering inside of Gephi, you should calculate the modularity. Just click OK. Then now we can change the color using this modularity score. It's a Rubin method. It uses the same one like Rubin method. Now we can see the 6 clusters. It's the same number of clusters we saw in iGraph. And click apply. It shows a cluster of 6, right? It's exactly the same number we saw in the iGraph. Let me look inside more details of the network here. I will just zoom up. So it seems like there's 2 different colors of the class here. When they get close together, it seems like they are in the same grade. Like here is the pink or purple, is a second grade class B. And how about the orange color? It's 2A, right? So let me change the colors for each of the classes. I will make almost a similar color for the classes in the same grade. So 2B will be more like orange. Apply it. Apply, so we can recognize they're in the same grade, right? And here 3A is a pink. And where's a 3B? 3B, yeah, I will make it like more, looks like a pink. Here it is. Yeah. And how about this green one? It's 1B, then where is 1A? 1A is black, right? But I was a little bit surprised to see that these two classes in the same grade at the first grade, they are pretty much distanced to each other, unlike the other second and third grade, right? But I will just make a change in color. I will change the black into more like green. Apply. Yeah. And this is the point where we can be confused. We have two gray colors, and 5B is blue one. Then how about this? I think this is 5A, and I will change the color into like blue. Applied. And this must be 4A. I will change it into like more green. So now we can see the cluster here. And the first grade and class A, class B, and class A is distance to each other. And for the first grade, class A and B tends to be distance to each other. But rest of the grades, the classes are really close to each other, right? Then let's compare this with the clustering community network. And we can see that as we expected, the classes in the same grade are clustered together almost like in the same class, right? But for the first grade, they are differentiated. They are in a different cluster. So that we cannot recognize by this, only the network picture, we can recognize that they're in the same grade. I think there must be some reason for that. It can be because of the school building structure, and the class of A and B must be distant to each other. But rest of the classes in the same grade, they are very proximate to each other. The physical distance must be really close. So let's say for the Gephi network visualization session. So we could find that Gephi is very versatile and even very effective network visualization tool. And it all depends on your skills, how to maximize kind of the impact of the visualization. You can choose your colors and the shape, and also you can calculate some of the network features and reflect some of the calculated scores into the clustering. So I hope this was real helpful to figure out how to use Gephi for your network analysis in the future. So this is the end of the second session and also end of the entire lecture for the network analysis. I hope you enjoyed learning from these video lectures. If you have any further questions and feedback, please send me an email to me. As I noticed in my GitHub repository before, this video will be open to the public from this June 2020 through YouTube and my personal website. Thank you so much for your participation and hope everyone will be safe and healthy.